every video. So they'll know the name of the book, so I don't have to tell them. Let's do voltage and current laws. Now let me talk about something called node. A node is actually a point that connects two or more elements. So a node, like something like this, you can have something, could be something attached here. We don't care what's attached. That's a node. It's connecting three elements. This is also a node. Notice it's connecting two. A node could look something like this. Like we're doing voltage sources, so in terms of something you can relate to. This is a node right here. Notice that point connects these three elements, because you can actually take these three and connect them like this. So that's really a node, and this is also a node. So all of these are nodes. Now a path, on the other hand, is if you were to travel from one spot and to get back to the same spot. If you look at that circuit here, let me put another one like this, but it's not connected, that end. So a path could be this path. You start from here, and you go around, come back all the way back here. That's a path. Closed, it's called a loop, actually. A closed loop. It has to be closed, can't be open. A path also could be you start from here, and you can go down here, come back right there. That's another one. You could have one inside this. You start from here, and you go around, you come back here. All these are paths or loops, closed loop. This is not a closed loop here, because if you travel that way, once you hit that spot, what happens? Nothing. So you can't use this one. This becomes useless. It's not going anywhere. You'll see that's an open circuit.
What's the definition of a path?
A path is defined as a point, like a node that you start from, you end at. You know, it's like a loop. A closed loop. That's really what a path is. If you start from one spot and you can travel and come back to the same starting point, that's what a path is. So the best way to write a path as a closed loop. So if you can travel, you start from one point, you travel and you come back to the same starting point, that's what a path is. The reason we're looking at that is because you're going to hear me using closed loop or path. You're going to hear me say node for voltage and current laws there. Kirchhoff. So let's talk about Kirchhoff, current law. Some people call it Kirchhoff, so it depends who you talk to. Sounds like a German name there. Spelling Kirchhoff. F apostrophe S, Kirchhoff's current law. I don't know if it's German. It sounds like it is German, I think. Robert Kirchhoff. 2 H's and 2 F's in his name. He used to teach at some German university there. And what Kirchhoff said about Kirchhoff current law, it says if you add the sum, well, I'll use the sum of all the currents entering a node is 0. That is Kirchhoff current law. What does that mean? He said entering, so you got to be careful with that. Let's say this is my node, and I just throw lines coming out of it. So let's say there's a current going in this direction. We'll call it I sub 1. This is I sub 2 going to it. Let's make this leaving that I sub 3. Let's make this one going in I sub 4. And let's make this one leaving out I sub 5. He said if you take all the currents entering that node is 0. Now, your first reaction, well, the only 3 going to that is I sub 1, I sub 2, and I sub 4, right? So is that equal to 0? No. What happens to I sub 3 and I sub 5? So, well, these are leaving. Well, I know they are leaving, but I can redraw them there. Notice this is leaving. I can reverse the direction of it and make it what? Negative I sub 3, I sub 4, and I can redraw this as going in as negative I sub 5. So if I use Kirchhoff definition there, if you add all these currents entering the node is equal to 0. So I sub 1 plus I sub 2 minus I sub 3 plus I sub 4 minus I sub 5 is equal to 0. Now, I don't want to reverse the direction every time I see a problem like this. So what I always say, which is the same thing, the current going into the node in, if you add them all, that's add them, should equal the algebraic sum of all the current leaving that node. That's another way of saying it. The math is exactly the same. So if you look at that node, if you add all the currents going in, what's going into that node? I got I sub 1, bless you, I sub 2, plus I sub 4. What's leaving that node? I sub 3, plus I sub 5. You know mathematically, if you brought these to this side, what will happen to them? They become negative. So I tend to use that one. That's what I use for Kirchhoff current law. Again, that's me. I go all the current going in equals all the current leaving. You can use either one. Nobody's more right than the other. Nobody's wrong, nobody's right. I mean, we're all right. So let's take an example on that and see what will happen. Let me see if I can find an example here. I'll try to save the problems in the book for you. So I'll try to get different problems, not in our book. So when you go home and look at the book, I can make something up there. Let's write some equation. Let's do this circuit. I'm going to make it ugly. Just looking wise, make it ugly. So here's my circuit. And again, this is a current source with the value, I don't know, what do you want to use? I sub A. I'm going to put 3 sources there. Let's say we have a resistor here, and we have a current here, we'll call it I sub 4. Let's put another resistor here, and we have a current here, we'll call it I sub 2. This is like a 2 ohm resistor. This is a 4 ohm resistor. That's how, by the way, I named them. When this is 4 ohms, I call that I sub 4. And this is 2 ohm, I sub 2, unless I get 2 of them. Then I got to change my... Let's say there's another one that goes like this. In parallel, well, it is in parallel. We'll talk about 1 ohm here, so it'll be I sub 1. And let me define that going in. I say I'm trying to make it ugly one intentionally. This is 5 ohm. So this is I sub 5 going. I'm making it going up there. Again, I have no idea which way it's going to go. I'm just defining them going that direction. We have another source here. We'll call that I sub B. I'm almost done with the picture. I have a resistor here. We'll say 3 ohms. So there's a current, I'm going to define it going that direction, I sub 3. And let's put another source here. We'll call it I sub C. Hello.
They must be doing it wrong. I got a quick question for you.
Yeah.
Downstairs, oh, what a beautiful picture.
Yeah.
Downstairs in 319, does that computer have the ability to show what's on all the other computers? It used
Yes.
to.
Yeah.
It does.
I think it does, 319.
Do you remember what the,
It's not
what was
vision.
it called?
It's not vision. It's a picture on the bottom.
There is a picture on the bottom?
Yeah, there should be. I know on 321 there's a picture on the bottom, but I think 319 too. I bought them for both.
I thought you
Yeah,
did.
but I don't know.
And I was trying to do it, and I'm like, well, then I don't know, somebody bothered
Yeah.
and interrupted me, and I thought if you were quiet in here, I'd come in. But, okay,
I'll go after the class. I'll look and see.
will you let
Yep,
me know?
Sure.
Thanks,
Yep.
thanks.
No problem. Okay. So let's look at the nodes. Usually we need to have a ground in the circuit. So which one you want the ground? Want to make this your ground? Doesn't really matter, one of them. You can pick any node. That could be that one, could be this, could be that one, the ground. So let's look at that node. That'll be a good ground here. There we go. That's ground. If you were building this in the lab, you got to attach a ground to it. Notice, by the way, this source is really, you can attach it right here. But we got a problem, that little short here. There's nothing here. Notice there's a wire attached across that. That's going to be a problem. We'll get to that later. So there's a node we call node 1. N1, node 1. So it's Kirchhoff current law, by the way, we call it KCL. Kirchhoff or Kirchhoff current law. KCL. At node 1. The top. Maybe I'll use capital N. Looks nicer. Well, it says all the current entering that node, so here we go. If the algebraic sum of all the current going into the node should equal the algebraic sum of all the current going out of that node. And now let's look and see what's going to node 1. What do we have going to node 1? I sub 1, yes. I sub 1, what else? I sub A plus I sub C, yes. And what's leaving that node? I sub 2 plus I sub 3. Good. Let's look at this node. Node 2. Again, KCL at node 2. The current entering that node, the algebraic sum of all the current entering the node should equal the sum of all the current coming out of that node. And what is going to that node? I sub 1 plus I sub 2, what else? I sub 1 is leaving, thank you.
I sub 5.
I sub 1 is leaving. I sub 2 is going in, plus I sub 5. And what's leaving that node? I sub 1 and I sub 4, if my eyes are seated correctly. Let's look at this node. KCL at node 3. What do we have going to that node? I sub 3 and I sub B, right? So the current going in equals the current coming out. I sub 3 going in, I sub B going in. What's leaving? I sub C. Now the bottom. There's any more? Let's look at the bottom right here. So that's node 4. I'll give you a little hint. That's going to be big. Notice what's attached right here. Wire, right? Just a wire attaching, right? Which is wire here. So that means this is actually one piece because there's no element. This is one node. All of that. So when you say the current going to that is the current going to the entire one. So you got to look from all ends and see what is going to it and what's leaving that one.
Would we have to do the same for node 3 then, or is it only node 4?
For node 3?
Yeah.
Yes, node 3 now, notice is attached right here. So what some people will do here, yep, we should add that to node 3 here, because that's all the pieces. We're going to look and see what's attached to it. So now, let me just finish this one, we'll come back and fix 3, which is the last set of pieces here. Because this node is the same point here. There's a wire attaching them. So what do we have going to it? We have what? I sub 1. Not I sub 1.
I sub 4.
I sub 4 plus what?
I sub B.
I sub B. You're going to see something, as I said, something is going to be funny about I sub B here. What else going to it? I sub 3. What else? What's leaving that node?
I sub B.
I sub B. And you know mathematically when you have I sub B on both sides, what happens? Cancels out. And what else?
I sub 5.
I sub 5.
I sub A.
I sub A. Do we have anything else?
I sub C.
I sub C. Where's I sub C? So you have, for node D here, Is there, where's I sub 2? Nope, that's not going to it, I sub 2. Now to go back to this one, if it's the same node now, since we said that's the same node connecting two or more elements, again, if you don't see that, watch this. If you don't see that's the same node, I should start with one not as bad as this one to start with for first one. Notice that that node is the same as right there, so I can really take this one, go right there with it, attach it right here. Now, this one is attached from 2 here back to here. That's the 5. Now what about that source? That source goes like this, back into it. Starts from that node and it goes back to the same node. That's why when we did the equation right here, that disappeared. So you have one node, node 1, node 2, and this will be node 3. The equation will shrink to 3, actually 3 equations, not 4 of them. So if I go write node 3 now, and I include that in it, guess what I'm going to have? I'm going to have this equation. Because if you look at that, oh, wait a minute, you forgot some pieces here. So what's going into that node? I only looked at that end, but I never looked at the whole thing. So if I look at the whole thing, what's going to it? I see I sub 4 going to it. And what's leaving that? Well, if it's the whole thing, I forgot to include that piece. What else I forgot to include? Where's I sub 5? Yep, I sub 5. I sub A is leaving. Anything else? Did we leave anything out? How about C? Where's C? I already have it going in, right? And notice now this one cancels this, and these two equations end up being the same. Are they the same? I sub 4 plus I sub 3 equals what? I sub 5, I sub A, and I sub C. It's the same node. But if I redraw that circuit like this, I would have known there's only 3 nodes, 1, 2, 3 in that circuit. So we could have just attached this one here instead of having another wire here. I could have just moved that point, just put it there, move this one there, you know. But it looks like we have 5, 6 nodes there, but it's not really, it's 3 nodes. This node and that node, 3 and 4 are the same. Node 3 and node 4 are the same. So these two equations are the same. When we put the nodes, we're looking like the voltage. Now, a short circuit has really no voltage. That's why the voltage of this node is the same node. So when we're doing like problem with that, we say, well, the voltage here is the same as the voltage here is the same as the voltage there. So we treat that as one node. Because just a wire connecting them. Technically, you said, well, if you want to do them as nodes, there's a node here, there's a node there. It connects 2 or more elements. That's a node. So if you don't want to treat them as one giant node, you can. Except now go, what is the current through that? Notice, if I don't want to treat them as one node, I shouldn't start with this one. I should start with a different one. Watch the math. If you treat them as separate nodes, start to get ugly now already. The picture, I mean. I'm not as nice, neat as before when I started the problem. Now, if you treat them as separate nodes, we had I sub 5 going this way. Same circuit, we have I sub 4 going in. Well, what's this current here? Do we know what that current is? Just because they don't label it, let me define something I called I sub x here. Let me define this as I sub y. I have no idea which way it's going to go. I don't know that. But if you follow the math now, this I sub b, I sub c, I sub 3, did I leave anything out? I sub a, I sub 1, I sub 2. Same circuit. Nope. Same, so I'm just copying that circuit. Since I don't know what the current through these branches, I call them I sub x and I sub y. Now, if you look at the math there, you go, let's look at that node. That node, what do we have? We have I sub 5 going to it, I sub 2 going to it, and what's leaving? I sub 1 plus I sub 4. Good. That's this node. No change. What did we call that? Node 2. Now, at this one node, well, this one's going to change now. This one, no change at node 1. But let's look at node, what did I label that? 3. At node 3, we have what's going in? I sub x plus I sub b and plus I sub 3, and what's leaving? I sub c. Node 4, I think the bottom. Is it 4? KCL at node 4. What is going to that node?
I sub y.
I sub y, yes. And what's leaving?
I sub 5.
I sub 5.
I sub b.
I sub b.
That's it.
That's it? Okay. Now play with the math. These are equations.
Would you also need to make the center node the N5?
N5. Want to do a note on that one? KCL at node 5. You want to do that? What do we have now? I sub 4 going to it. What else? What's leaving?
I sub a.
I sub A,
I sub x.
I sub x,
I sub y.
I sub y.
That's
Okay.
between equal signs.
Oh yes, equals.
I sub 4.
Now let's do some algebra here. You'll see why we treat that as one node. Remember that equation? Let's look at I sub y. What is I sub y equal to from this equation? I sub 5 plus I sub b, right? Let me find out what I sub x is equal to here. What is I sub x from this one? Isn't that I sub c minus what? I sub 3 plus I sub b? Minus I sub b, yes. So do a substitution. I sub 4 equals I sub a plus, in place of I sub x, I'm going to put what? I sub c minus I sub 3 minus I sub b. In place of I sub y, I'm going to write what? I sub 5 plus I sub b. I can see the I sub b is going to cancel. Can you see him? So if you play with that, I can take the negative I sub 3 to this side, and that becomes what? I sub 3 plus I sub 4 equals what? I sub a plus I sub c plus I sub 5. Do you agree with that statement, the math? Now watch when we did that equation. When I treated that as one node, look what I got here. I sub 4 plus I sub 3 equals I sub a plus I sub c plus I sub 5. Is that the same thing? See that? That's why when you only have wires, that's treated as one node. Instead of 3 separate nodes, then I got to do all this extra math, which I can. Or I can treat it as one node, and that eliminates 2 of the equations already. It takes me to the answer in 1 step. Let me take a normal one instead of ugly one like that to start with. And that was a poor judgment by me to start by that. I mean, with that problem. But it's all right. Let me see if I can find another one. The back there, maybe I can find something in the book there quickly. Do we have anything here? Okay. Not really. Okay, I'll do this. I'll make one. Let's put 10 volts here. This is resistor 1. I might come back, give you some numbers for it. Maybe, maybe not. This is resistor 2. This current, I'm going to tell you it's 2 amps. This is resistor 3. And this is 5 amps. Let's call this current here I.
Those resistors have like a value, or you just...
What is it?
Like, do those have like a specific value, or you just...
Well, I'm just leaving them blank intentionally. The only thing I'm going to do is, assume this current coming out of this is 3 amps. Just given that circuit. Now, if you look at this circuit, not counting ground, there are 3 nodes. Can you tell me where the nodes are?
Top and bottom.
Okay, this is 1. This is the ground. We never really count the ground. So there's the ground. That's good. That's 1 node. You said the top. Well, which top? Where?
Top left.
Here? There's 1. Node 1. There's another one. That's node 2. So I got 3 nodes. If the current going through the source is 3 amps, that current leaving going that direction has to be going that direction. I already gave you a hint that's 3 amps going that way with the picture. But if you have 3 amps going up there through the source, we'll call it I sub 1. If I do KCL at node 1, it says the current going to that node, which is what? 3 amps, should equal the current leaving that node, which is what? I sub 1. So I sub 1 is 3 amps. Now I do KCL. The question is to find I. That's what the question is. KCL at node 2. What is the current going to that node? The sum of the current going into the node should equal the sum of the current coming out of that node. What is going to that node?
5 amp and I.
5 amp plus I sub 1. And what's leaving that node? 2 amp plus I. But wait a minute, we just calculated I1 to be what? 3 amps? Eight minus 2, which is what? 6 amp. That's what the current will be. So that's Kirchhoff current laws. The algebraic sum of all the current entering a node, or any node, should always be 0. Any node. And again, think of a currents like water. Whatever goes in must equal what comes out, unless there's a hole in it. Because you can have at home, you can have a hose, and you might decide to break down by one of those junctions that the water will go in both directions. But that water coming in this direction is going to split. And if there is no leak in that hose, that water coming in should equal to the sum of these two. Whatever goes in must equal what comes out at that junction. Current is the same thing. The only difference between water and current, if you put a hole in the hose there, what will happen to the water? The water comes out. If you take a wire and cut it, there is no current dripping down. That's it, nothing goes through it. That's the only difference. So this is Kirchhoff current law. Let's try Kirchhoff voltage law. 2 H's, 2 F's. Which is KVL. And again, he said the algebraic sum of all the voltages in a closed loop, closed path, whatever you want to call it, is 0. The algebraic sum of all the voltages in a closed loop is 0. So for example, if I have here plus to minus, I'm not telling you what that is. We'll call it V1 plus to minus V2 minus to plus V3. I made them crazy shapes. I don't want to know what's in them. Something attached there. Notice this is a closed loop, so if you can start from one point, go around, come back to the same point. And it doesn't matter which direction you go. So I usually tend to draw direction. I'm going to move in that direction, clockwise. But you can do counterclockwise, doesn't matter. Now notice some of these you're entering minus to plus and some plus to minus. So we're going to decide which one is positive, which one is negative. Our book probably uses minus to plus as minus, plus to minus as negative. I like to stick with the sign I enter. It makes my life easy. I'm going to go minus to plus as minus, plus to minus as positive. It's an equation. So in this case, since I'm entering the minus, I'm going to say negative V1, add to it. Notice I'm entering the plus, let's add to it. V2, I'm entering the negative, minus V3 is equal to 0. Again, our book might do them differently. They might go, I'm going to call this a minus V1, a plus V1. The minus to plus, they'll call plus, and this is minus. Is this one wrong? No, because if you take this equation, that's an equation. And if you multiply every one by -1, what would you have? You'll have that equation. So it doesn't matter which way. I tend to go minus to plus as minus, plus to minus as positive. It makes my mind straightforward. I don't have to think, oh, minus to plus, oh, that's a plus, plus to minus, oh, that's a minus. Like I'm thinking backward. I'm entering the negative, that's minus, entering the plus, that's a plus. Much easier for me. Where we use this a lot, I'll show you. And I talked about this already. Let's say this is 10 volts. This is 5 ohm. And let's say I ask you, what's the current here? What is the current going through that? There's only one current going through this. Now we said these two are connected in what?
Series.
Try again. Parallel. Notice the top and the bottom attached. The top is attached, the bottom is attached. That means they should have the same voltage. And nobody questioned me last time why they should have the same voltage. Well, let's think about Kirchhoff voltage law. If we travel this way, let's call this voltage VR. KVL, it says if you travel, let's travel this way. If we travel in a closed loop and you add all the voltage, it should be 0. I'm entering the minus, I'm going to use that a minus. Minus 10. I'm entering the plus, that's plus VR, should equal to 0. What is VR equal to then, mathematically here? 10. It's the same as this. That's the reason why when they're in parallel, they have the same voltage. Now the question was find I. Didn't say find R or VR, find the current. There's only one current going through that loop there. Only one. So how do we find that current? Ohm's law, yes. You know the voltage now, V equals what? I times R. What's the voltage? 10. What is I? I'm looking for it. What's R? 5. I equals what? 2 amps. Let's try another one. I decided to stick with easier examples instead of tackling an ugly one like earlier today. Let's take that circuit. Again, this is 15 volts. This is 5 ohm. This is 8 ohm. This is 7 ohm. And the question, now, how are these connected? Yes, they're not connected in parallel. Notice the top of this, or this tip attached to the end of this one, the beginning of this. The end of this attached to the beginning of this, the end of this attached to that. So there's only one loop in that circuit. There's only one. That means there's only one current going through it. It's going to travel. And remember, if you only have one source, we said the current is going to go from minus to plus through the source. Why does it go minus to plus through the source? So the source can do what? Supply the power. And the question is, what's the current through that? Like, I don't know, you got a lot of resistors there. Well, let me call this voltage here V1. And notice I labeled plus to minus. Why? Because the current is going to travel in that direction through the resistor. It's going to mark it plus to minus. Why is it plus to minus? Positive current entering a positive terminal is going to make that resistor absorb the power instead of supplying. So this will be plus to minus V2 plus to minus V3. Let's do KVL. Minus to plus, that's a minus 15, plus V1, plus V2, plus V3 is equal to 0, which means V1 plus V2 plus V3 equals to what? 15. That doesn't solve for I for me. I need to find I. We got a problem. We got 3 unknowns in that equation. None of us can solve one equation with 3 unknowns. So what are we going to do?
Could you solve for total resistance and then get the total current?
What's the total resistance? How do we know what that is? Sam?
It'd be 20 ohms, I don't know.
How'd you know that's 20 ohms?
And that's series resistors.
Well, the reason you're going to add them is correct. I'm trying to find the reason you add them when they're in series, because if you look at them, notice Ohm's law says V1 equals I times R sub 1. Right? It's whatever this current times that resistor. Well, that resistor happens to be what? 5. I times 5. That's what V1, which is 5I. What's V2? Ohm's law again. It's the resistor times the current. That's 8I. What's V3? V equals I times R. I times 7. What's I times 7? 7I. So if I replace each one by its value, notice if you factor an I out, what's left? 5 plus 8 plus 7 equals 15, which tells you when you have resistors connected in series, to find the equivalent of them, what do we do? Just add them. But that's the math behind it. That's why we add them. So 20I equals 15. What's I equal to? Is it 0.75 amp? So that's why you can add them when they're connected in series, because of that logic. Let's have fun with the Kirchhoff current law, Kirchhoff voltage law. Let me just throw some circuits there, ask some questions, see if we can solve them. So I have a resistor here, and I don't know the value of R, and I could care less. I know the voltage are minus to plus 4 volts. I have an independent source here. The value of that, 36 volts. I have a resistor here. I don't care about the value of the resistor, VR2, because I call that resistor R sub 2. You know what, I'm going to call it V2. I don't even want to mention R. V2 is good. And I'm going to label plus on the top, minus on the bottom. I have another resistor here. I don't know the value of it. Again, don't care. Plus to minus 12 volts. I have an element here, attached here. I don't know what that is. All I know, the voltage plus to minus 14 volts. Let's call this point A. I have another element here, minus to plus, what should we call it? Vx. I have a voltage source down here, V1, and let's call it Vs instead of V1. I have a resistor here, and let's call that plus to minus V1.
What's in the top right corner? Can you like slide it down a little?
Top right corner. Got it now? That's Vs here. Let's begin the first question by saying, what is V2? Let's call this one B here. This voltage, by the way, here, Vx, is this voltage right here, value-wise. Let's call that Vx. The voltage here between A and B, value-wise, is that number right there. So let's find V2 first. How can I find V2? That's this voltage right here.
KVL,
KVL where?
loop to the left.
On the left? Sure. If you take KVL on this side, left side, that's this piece. Sum of the voltage in a closed loop is 0. So algebraic sum of all the voltages in a closed loop is 0. That's what that means. Add all the voltages in a closed loop is 0. That's not VI like entering. It's not in. V1, V2, V3 is subscript, you know. So if we do that right here, again, plus to minus, let's follow that convention. I'm going to travel this way. I'm going to enter the plus. I'm going to make that plus 4. I'm going to enter the minus, minus 36. I'm going to enter the plus, plus V2 is equal to 0. What's V2 equal to? 32 volts. Now, second one, find Vx. That's this voltage right here between A and B. Well, to find the voltage, if you're in the lab, you take the probe, you attach the plus on the top, the minus on the bottom, the red one on the top, the black one on the bottom, and you measure the voltage. So let me do a KVL inside that little piece. Assume the probe is attached there. The digital multimeter is attached right here. So it's going to be negative V2 plus 12 plus 14 plus Vx should equal to 0, plus to minus. Everyone see that? So I'm taking a wire here, and attaching it to my device to see what that voltage is. So that's why this is a plus Vx. So do the math here. We know what V2 is, 32, so that's negative 32 plus, what is that, 26? Plus Vx is equal to 0. What's Vx equal to? 6 volts. Now let's look at the right side. Right here. Let's say find V1. Let's do a loop right here. That's where V1 is. So if you try to take the outside, you couldn't because you don't know what Vx is yet. So if you start with the outside loop, this whole loop, go, I don't know what that voltage, so I have two unknowns in one equation, you couldn't solve it. But by breaking it down to this part and that part, or now you can do the outside, then you can do it. So if I take this one here, or the whole thing, it doesn't really matter. This is less work here. That's negative Vx minus Vx minus Vs plus V1 is equal to 0. I know what Vx is. Isn't that 6? Negative 6, negative 6, negative Vs, that's the source. And V1 will be what? Is whatever the source plus what? 12 volts. So you tell me what is that source value. I never gave you a number for that. So if I give you a number for it, I can tell you what the answer. Let's say the source was 7. So if the source is 7 volts, now what's V1? 7 plus 12, which is 19 volts. If the source was 3 volts, it will be 3 plus 12, which is 15 volts. So whatever that source is, you add to it 12, and that's what V1 is going to be. Okay. So this is KCL, KVL. My only regret, I wish I didn't try the first problem I did today. It's all right, that ugly one. You're going to see ugly ones like that, but I wish I waited on that for a while till, you get your feet wet in that one. But oh well.